So I was hoping that we might be able to have our test Thursday. I'm not sure that's going to work just because of what we have to go through, but I'll figure that out for sure by the end of today. See how much we get done. So we're going to finish off by looking at solving some logarithmic equations and verifying solutions. We'll see that in some cases when you solve equations, you're going to get extraneous solutions. So those are solutions that when you solve the equation, you get the answer, but when you check it, it doesn't work. So we'll look at solving exponential equations in which the bases are not powers of one another. We're going to be looking at problems involving exponential growth or decay. We'll look at some problems involving application of exponential equations to loans, mortgages, and investments. And then finally looking at modeling a situation with an exponential or logarithmic equation. So let's start by looking at solving some logarithmic equations. A logarithm expression is defined for only positive values of the argument. We've talked about that, right? You cannot take the log of 0, you cannot take the log of a negative number. When we solve a logarithmic equation, it's essential to verify that the solutions do not result in the logarithm of a negative number. Solutions that do this would be called extraneous and are not valid solutions. So we're asked to solve these equations. We'll give answers as exact values. We'll verify our solutions. And then we'll also look at what the restrictions on the variable are. So we're going to be looking at two different types to solve. The first type, like these first two examples, are where every term is a log. We're also going to see some equations where one term might not be a log. It'll be an actual number, an integer. But for these ones, all the terms are logs. So our first step will be to simplify. So we have both sides expressed as a single log. And we can do that on the left side here because you're subtracting logs with the same base. You can use the quotient law. This will be the log of x over 15 equaling the log of 0.2. So that's going to be our first step. When all the terms involve logarithms, we'll simplify so that we get both sides expressed as a single log. Now, these two sides are equal. We are told that at the start. Because both sides have logs with the same base, they're both logs with a base 10. Because those parts are the same, the other parts will be the same as well. They will be equal as well. So we can go our next step saying that x on 15 equals 0.2. We're not really doing a mathematical operation to get this. It's not like we're dividing both sides by log base 10 because you can't do that. But what we're saying is we are told the two sides are equal right from the start. Once we get the left side expressed as a single log that has the same base as the log on the right, because the two sides are equal, and also because they're both logs with the base 10, because those parts are equal, the other parts will be equal as well. And those other parts are the x on 15 on the left equaling 0.2 on the right. So again, it's not a mathematical operation that we're using here. We're using principles of equal equations. So now we can solve for x by multiplying both sides by 15. So we'll multiply the left side by 15 and the right side by 15. We do that so that the 15s can cancel on the left. And so you'll have x equals 0.2 times 15, which is 3. So there's our solution. Our restriction. We look at each term, and it's only the first term on the left that has a variable. And remember, you cannot take the log of a negative number, nor can you take the log of 0. So because the argument of that term is just x, our restriction is that x has to be greater than 0. So our answer is not outside that restriction. It is a number greater than 0. So that doesn't eliminate that solution, but we will check to make sure that it actually works. If we take the log of x on 15, which is our original expression, equaling the log of 0.2, if you let x equal 3, You'll get the log of 3 on 15, which is the log of 0.2. So that gives you the same value that's on the right. So we know our answer works because you get the same expression. Okay? Now, the next one. Once again, you've got every term expressed as a logarithm. So we can simplify using the laws of logarithms to get both sides expressed as a single log. In this case, with the same base, the base of 4. So on the left side, because you're subtracting those logs, that's the quotient law. And on the right side, because you're adding those laws, that is the product law. So you're going to have log base 4 of x over x minus 2 equaling on the right log base 4 of 3 times 5, which is 15. And now because we have both sides expressed as a single log with the same base, log base 4, and because the two sides are equal, if the log base 4 parts are the same, then the other parts must be the same as well. X over x minus 2 has to equal 15. And now we can solve for x by multiplying both sides by x on 2, which is the same thing as if we made the right side a fraction and then we cross multiply. So you're going to have 15x take away 30 equaling x. If I subtract the x from both sides, I'll get 14x on the left, add the 30 to both sides, and then divide both sides by 14. X will be 30 on 14, which is 15 over 7. My restriction here. In this case, I have two arguments that I need to look at. I've got an argument of x, so x must be greater than 0. I also have an argument of x minus 2, which must be greater than 0, so x would have to be greater than 2. Like we did before, we would want to take the statement that satisfies both of those conditions, which would be that x must be greater than 2. That is our restriction. And our answer of 15 on 7 is greater than 2. So we know that the restriction won't eliminate that solution, but we should still check it using the original expression. Which I'll use a simplified form of the original expression, which was that there. Okay. So I will have log base 4 of 15 on 7 over 15 on 7 minus 2. That should equal log base 4 of 15. So as I simplify on the left, I'll have 15 on 7 divided by, it'll be 15 on 7, take away 2, which is 14 on 7. So I'll have log base of 15 on 7 divided by 1 on 7. Dividing by a fraction is the same as multiplying by the reciprocal. 7's cancel, and you have log base 4 of 15. The same thing as what's on the right side. That shows that our solution is correct. Okay? So these next ones are examples where one of the terms is not a log. But the left side, both terms are logs, so we can use the laws of logarithms to simplify, to combine them. Because those logs are added together, that is the product law. If you multiply out those binomials, you'll get x squared minus 2x minus 3. And now we have two options. If you wanted, you could make the right side a log. The log on the left has a base of 5. You would need to write an expression on the right, which is also log with a base of 5, but that expression must equal 1. So that would be log base 5 of 5. You could do that. That's the same as 1. And then you would drop the log base 5 from both sides and simplify or solve with what you're left with. The other option, though, is to convert from logarithmic to exponential. Start with the base and cycle through. You're going to get the same expression. You're going to get the same expression if you made the right side a log by writing it as log base 5 of 5 and then dropping the log base 5 from both sides. You would get this expression right here. So, got a quadratic, need to make it equal to 0 by subtracting the 5 from both sides. There's the quadratic that we now need to solve. And we solve quadratics by factoring normally. The factors will be x minus 4, x plus 2, which gives us answers of positive 4 and negative 2. If you look at the arguments, x cannot equal negative 2. It is extraneous. Because if you let x equal negative 2 in either of these arguments, you'll get the log of a negative number, which we can't have. But we can also get our restrictions by taking each argument and saying it must be greater than 0. So therefore, x must be greater than negative 1 is one of those. The other argument, x minus 3, must be greater than 0. So x must be greater than positive 3. Again, you need to take the one that satisfies both, which is that x must be greater than 3. That is our restriction. And our answer of 4 is yes. How does negative 2 become negative 8? Because you subtracted 5 from both sides. Okay? Now we checked the previous ones by checking them manually. This could also be checked graphically if you wanted to. So y equals would be the left side of the equation, which is a log. So log base 5 of x plus 1 plus another log base 5 of x minus 3. That's our first equation. Our second equation will just be y equals 1. That's the right side of that equation, 1. So zoom 6 to set our windows to their standard settings. We're looking for the point of intersection, which there is one there. Second function trace, number 5 for intersect. Now, right now it's asking us to identify the first curve that has x equals 0, but there is no y value because that log equation doesn't start till over here where x is greater than 0. So we need to use the right arrow key and scroll over until we get a y value displayed. There we go. Now we can verify that that's our first curve, our second curve, enter, and our guess, and you'll get your answer of 4. So there's another way you can check to make sure your answers are correct. check them algebraic or graphically. All right, question B. I would collect the logs together first. These are both logs with base 10, common logs because no base is indicated. So I would subtract the log of x plus 1 from both sides. And then you can use the quotient law here to combine into one log. And then like we did before, I would convert from logarithmic to exponential. This is a common log on the left, base 10. When you start with the base and cycle through, it'll be 10 to the power 1, which is 10, equaling 8x plus 4 over x plus 1. When you cross multiply, it'll be 10 to the power x plus 1 equal 1 to the power, or 1, excuse me, times x plus 8x plus 4. 10 times x plus 1 equals 1 times x plus 4. So in this case, we don't have a quadratic to solve, so we're not going to have to factor. But we can subtract the 8x from both sides, which will give us 2x on the left. We can subtract the 10 from both sides on the right. 4 take away 10 is negative 6, so x will equal negative 3. Now, just because you have a negative answer doesn't mean it won't work. We have to check and make sure what our restrictions are. So our first argument, 8x plus 4, must be greater than 0. So 8x must be greater than negative 4, and x must be greater than negative 2. So now we know that our answer won't work, because negative 3 is not greater than negative 2. But just so we can state the restrictions on the variable, let's find our other restriction. It comes from the argument x plus 1 must be greater than 0. So x must be greater than negative 1. We would need to use a restriction that satisfies both, which is x is greater than negative 1. All numbers greater than negative 1 are also greater than negative 2. But again, that's also a reason why our answer does not work. So this is extraneous. There is no solution. X equals negative 3 is extraneous. Kind of ran out of room here, so and once again, that could be verified graphically. If we put both of these equations in there, because the logs are common logs, I can just use the log button. Log of 8x plus 4. Close the bracket. There's equation 1. Equation 2 will be 1 plus the log of x plus 1. So we graph, and it looks like there's a point of intersection, but let's check. Second function trace. Number 5 for intersect. Enter, enter, enter. There is no point of intersection. Okay, everything is inputted into the calculator correctly. There is no point of intersection. So again, that confirms that there, is no solution. All right, looking at question C. Again, I would simplify by collecting the logs together. I would add log base 2 of x minus 4 to both sides. And that just leaves us with the number 3 on the right. On the left, I would use the product law to simplify because you're adding logs with the same base. You can simplify on the left by multiplying out the binomials. And then once again, we will convert from logarithmic to exponential. We'll start with the base and cycle through. 2 cubed is 8. We're going to subtract the 8 from both sides, and we'll get x squared minus 10x plus 16 equaling 0. We would solve this by factoring. The factors are x minus 2, x minus 8 equaling 0. So our solutions will come when each factor equals 0. And that gives us two answers, positive 2 and positive 8. If we look at our restrictions, x minus 6 must be greater than 0, so x has to be greater than 6. So that eliminates positive 2. That is extraneous. Our other restriction comes from the other argument of x minus 4. That must be greater than 0. So x has to be greater than 4. We would take the restriction that satisfies both, which is x must be greater than 6. The answer we got of 8 is greater than 6, but we will check it. And once again, I'm going to check it graphically. So equation 1 will be the left side, which is log base 2 of x minus 6. And if you don't have the newer operating system, that's fine. You just have to use the change of base identity. Log of x minus 6 in brackets divided by the log of 2. The right side will be 3, try that again, 3 minus log base 2 of x minus 4. So we graph and confirm the point of intersection. So again, we need to move over with our arrow key so that the y value appears because of the domain of both of these graphs. There we go. Enter, enter, enter. And there we get our answer of 8 confirmed. So there's our correct solution as well as our restriction below. Now for question D, you've got both sides expressed as a single log. Probably what I would do first though is I'd simplify. I would use the power law and bring the exponent 2 in front. Then I can divide both sides by 2. So when you divide both sides, you're going to be left with 2 on the right. And now I would convert from logarithmic to exponential. Start with the base and cycle through. So 4 will equal x plus 3. And when you subtract 3 from both sides, we get x equals 1. Our restriction is that x plus 3, the argument, must be greater than 0. So x would be greater than negative 3, which our answer is. We will check by, again, graphing. So the left side will be log base 2. My argument is x plus 3, and that is squared. The right side is just the number 4. Now this actually shows 2. Let me just check that, make sure that's in there right. Log base 2 of x plus 3 all squared equals 4. Yep. Now you can see it looks like there's 2 points of intersection. So that confirms that one is. If I put my guess in at -3, it does say -2.75, which is greater than -3. So that should work, but we didn't get that answer in our equation. So that means that it's extraneous. One more time. Log base 2 of x plus 3 all squared. Yep. Everything's in there correct. But we didn't get that answer on our equation. So I'm gonna go back and look at that again after the lesson one more time. Just go through it. But let's continue. If I find something haywire with that, I'll address it. Okay, question E. I would combine the logs like we have been doing by adding both sides to both sides. And then we can use the law of logs to combine those two expressions. Because they're being added, that is the product law. So when you multiply those out, you'll get x squared minus 2x minus 8. And once again, we will convert from logarithmic to exponential. We'll start with the base and cycle through, which will give us 49 to the power a half equaling x squared minus 2x minus 8. Power a half means square root, so it's the square root of 49, which is 7, equals x squared minus 2x minus 8. And again, to solve quadratics, we always want to make them equal to 0. We will subtract the 7 from both sides, will give us minus 15 on the other side. And this can be solved by factoring. The factors are x minus 5, x plus 3. So our solutions will happen when each factor equals 0. So that gives us positive 5 and negative 3. Okay, sorry, I got a mistake here because it's going to be 4x minus 2x. It should have been positive 2x. Should have been positive 2x. Which means it's x plus 5 and x minus 3. So x plus 5 equals 0. X minus 3 equals 0. So x will equal negative 5 and positive 3. If we look at our restrictions, our argument of x plus 4 has to be greater than 0. So x is greater than negative 4. We also have an argument of x minus 2 that must be greater than 0. So x has to be greater than positive 2. Again, we want to choose the restrictions that satisfies both, which is that x must be greater than 2. So that eliminates negative 5. We can cross it out to show that it's extraneous. So this is saying we have only one solution that should work, and that would be that x must equal 3, which we can check on our calculator. So the left side is log base 49 of x plus 4. The right side will be 1/2, which we can just write as a decimal, 0.5, minus log base 49 of x minus 2. Graph it. Looks like there's only one point of intersection. When I hit enter, there's no y value for the second curve because I need to move my cursor over because of the restriction on the domain there. And there we get our answer confirmed of x equals 3. Okay, going to stop there for today. I'd like you to work on those questions. Practice. I will post those in the classrooms for you to check your work. And remember, the assignment from Friday on page 402 was due for marks. So that's got to be handed in. Okay?